In this video I'm going to solve interesting theorems proof. Okay, so this theorem is very important because there are lots of questions that came in different type of exam like TIFR, JAM also, which is an application of this theorem. Okay, uh, so that's why I'm thinking that this theorem is very beautiful and very important to know. So I'm going to not just going to state this result but also trying to prove it. Okay, let's see. Proof. So the theorem says that any subgroup of R plus is either cyclic or dense in R plus. Okay, so subgroup of R plus means R is an additive group, set of all real numbers. This is an additive group. So if you choose any subgroup of R plus, that means it is a subgroup under addition, that is either cyclic or dense in R. Okay, so let H plus be any subgroup of R plus. If H is trivial, then we are done, because if H is trivial then it is cyclic. Assume that H is non-trivial. That means there is a state A not equals to 0 that contains is in H, which implies minus A also contained in H, because H is a subgroup. That means if A is there, minus A also there, because 0 is the identity element. So inverse of every element must be inside that subgroup. So A is in H, that will imply that minus A also belongs to H, right? That hence H intersection R plus means set of all positive real numbers, that must be non-empty, because if A is positive, then already A inside H intersection R plus. If A is negative, sorry, if A is negative, then minus A is positive, which is inside H and which is a positive real number, because I already assumed that A is non-trivial, I mean A is non-zero element. Okay, so that means H intersection R plus is not non-empty. I'm sorry, it's non-empty. Okay, because either A or minus A must be H intersection R plus, right? That means consider W be a set X belongs to H such that X is in H intersection R plus. So this is inside R, this is a subset of real number. Okay, so W is bounded below, right? Because X is in R plus, that means X is positive real number. That means clearly all the elements are greater than 0. That means W is bounded below. By completeness property of R, W has an infimum, right? W has an infimum. Let say, what should I use? U equals to infimum of W. Okay, this is a number. Case 1. So since W, all the elements of W are positive, so infimum is either 0 or a positive number. It cannot be negative. That's obvious. So case 1. Let U greater than 0. Okay. So I am considering the two cases. One is U greater than 0 and one is U equal to 0. So first case 1 is U greater than 0. Okay, then I have to assume subcase. Subcase 1 is U inside H, or U doesn't belong to H. I am taking infimum, right? I am taking infimum, so it might happen that infimum inside that set, or it might happen that infimum is not inside that set, right? So two cases are possible. So I am first assuming that infimum is inside that set. Okay, then what is happening? So if U belongs to H and U greater than 0, that is obvious, right? U belongs to H and U greater than 0. So then KU belongs to H for K belongs to natural number, because H is a subgroup. So U belongs to H, that will imply that U plus U, 2U belongs to H, 3U belongs to H. That means all KU for all natural number K is inside H, right? Let's draw a picture. This is real line. Say this one is 0, say this one is U, this one 2U, this one 3U, this one 4U, so on. Dot dot dot. Now by definition of infimum, by definition of infimum, for any epsilon greater than 0, there exists an element x belongs to W such that x belongs to so W is bounded below, right? So x belongs to U comma U plus epsilon for any epsilon greater than 0. That is by the definition of U, right? So in particular, so let's draw another picture that will be helpful for you to understand. Okay, let's draw this one. So here we have 0, we have U here, we have 2U here, we have 3U here, and so on. Now for any epsilon greater than 0, there must be an element x such that inside U, right? By the definition of infimum. Okay, that inside. So I'm taking, sorry, I should take this, right? Now let epsilon equals to this one. This is your epsilon, right? This is your epsilon. If here is an element, if x belongs to here, that means x in H, U belongs to in H, that means x minus U also belongs to H by the definition, since it is subgroup, since H is subgroup. Now what is x minus U? X minus U is this one, which is less than epsilon. So that is inside H, which contradicts that U is an infimum. Contradicts that U is an infimum, because I can choose epsilon to be very small, right? I can choose epsilon to be very small such that is already less than U. I can choose epsilon to be here, right, very small, and for that also it should satisfy this, right? So that means U is an infimum. That contradicts U is an infimum. So it is not possible, right? It is not possible. So it is only possible if x is equal to U itself, because I have to choose that x belongs to W such that x belongs to closed interval U comma U plus epsilon, right? So in particular, if x is itself W, then we are done, because x equal to W means it is always W. If x equal to U means it is always U, right? So if I choose any epsilon, whatever epsilon I can choose, whatever small epsilon I can choose, that also, then I can particularly choose x is U, and then x minus x, which is 0, that is inside H. So that is not a issue, right? So the only case, hence x equal to U is only possible case, which is imply that there is no element inside U and 2U, right? Because if there is an element between U and 2U, that will give an another this type of situation, right? So there doesn't belong to any element this type. So that means That means we have only u, 2u, 3u, so on. And H is a subgroup, so that will imply that minus u there, minus 2u there, minus 3u there, so on. And 0 is already in H. That means H is cyclic group generated by u. This will imply H is cyclic. So I have to show that it is either cyclic or dense. So two cases are possible. So in this case it becomes that H is cyclic. Okay. In any step, if you can't understand, then please mention the time and comment that in this line you can't understand. I will explain. Okay. Don't need to be worried. But it's a very important theorem. You should understand the proof. So that is the case. Try to think geometrically. Okay. So this is the case. So this is the case. Now what the other case left here? So A in particular, H becomes cyclic, right? Now case 2. So here is the subcase U belongs to H, right? Now if U doesn't belong to H, okay, there is another case. If U doesn't belong to H and U is equal to infimum of W, right? That means choose sufficiently small, same case, small epsilon greater than 0 such that epsilon is less than U. I can choose it because U is a positive number. I am already assuming. So I can choose epsilon to be smaller than U. Then by definition, there exists a x belongs to W such that U less than x less than U plus epsilon. Now x cannot be U because I already assuming that U doesn't belong to H. So x cannot be U. So it is strictly greater than U and strictly less than U plus epsilon, which will imply that x minus U is strictly less than epsilon, and this will imply U cannot be infimum, right? By the same thing, if you here 0, here U, here 2U, same thing. If you sufficiently small epsilon, you can choose, then you can always find. So you can choose an element here, you can choose another element here, right? That is because you can vary epsilon. You can take here epsilon 1 and then again epsilon 2. For that you can choose x1. Say here you can choose x1 here. You can choose again epsilon. For that you are choosing x2 here, epsilon 2, which is again very small. You can choose that, right? You can choose that. And then x2 minus u is inside in less than epsilon minus 2. That will imply x1 minus x2 strictly less than epsilon minus epsilon 2, right? Which is a very small quantity again. So that will imply, since x1 is in H, x2 is in H, that will imply x1 minus x2 is in all H, because of H is a subgroup. So hence this small quantity, this small real number, that is also inside U, which contradicts that U is an infimum of W, because I am already assuming that U is the infimum of W, where W contains all the positive real elements inside H. Okay, understand? That is the case. So in this case, this is also this is not possible. Hence, so both case we can conclude H is cyclic. Okay, H is cyclic. Now say another case. Now case 2. So it is completely, you have to think it geometrically, and then you have to use the property of infimum and property of subgroup. Okay, think it geometrically, then you can easily solve it. Okay, now case 2. So what I can do with case 2? Case 2, so the only case left if U equals to 0. Okay, so if U equals to 0, U is infimum of W, then U doesn't belong to W, because I am assuming W to be set of all positive real numbers which inside U, which inside H. I am assuming U equal to 0. That means 0 doesn't belong to W, right? 0 is in H, but 0 doesn't belong to W. I am considering all positive elements. So that means then for any epsilon greater than 0 there exists a x belongs to h depending on epsilon definitely, such that the same case 0 less than x less than epsilon, because 0 is the infimum element, right? 0 less than x less than epsilon, right? Now if x is there, then kx also belongs to h. If x is there, kx also belongs to h, since h is a subgroup. H is subgroup. H is subgroup, right? So what I got, that depending on epsilon, small epsilon, sufficiently small epsilon I can choose, then also there must be an element x which is inside epsilon, right? Claimed H is dense. Okay, let's draw a picture to show H is dense. We need to show any open interval in R intersects H non-trivially, right? Non-trivially. Okay, so let's draw a picture. See, this one is straight line. Okay, I'm doing for positive. For negative it is same, because H is a subgroup, right? So if x is a positive real number which is inside H, then minus x is a negative real number which is inside H. Okay, so for negative section everything will happen in the same way, so we don't need to worry about. So in particular we can do it for positive number. Okay, so the positive interval, choose any interval, right? You can choose any interval. Okay, you can choose any interval. Now this interval has a length, say this is a, this is b. This interval has a length, say b minus a, right? Now take epsilon to be b minus a by 2, right? Say this one is epsilon. Okay, this one is epsilon, right? By the previous property I can choose, say this one is epsilon, I can choose an element x which lies here. I can choose an element x which lies here. Choose x such that x in H, in particular in W, I can choose particularly for this, because this is the property of P. 0 is an infimum. I am considering the case 0 is an infimum, and I am already seeing that this, for any epsilon greater than 0 I can always find the x such that 0 less than x less than epsilon, right? I can always choose. So that's why in particular I can choose some x, so such that whatever epsilon I can choose, I can always find some x that's inside this, right? Now 0 is in H, x belongs to H, that means kx belongs to H for any x, right? So in particular here x, say here is 2x, here is 3x, here is 4x, 5x, so on. So there must be some kx here, right? So there must be some k tilde natural number such that k tilde x belongs to this open interval, and k tilde x also belongs to H. That means H intersects this open interval non-trivially. This will implies that H is dense. Okay, why? Because you can do the same thing for negative interval, because this is a subgroup, right? So whatever you can particularly choose this type of interval, and you can take this type of element, right? So since then you can do the same thing, because you can also do the same argument for negative real numbers. You can again consider some w tilde, which is set of all, say, y belongs to h, such that h intersection y belongs to h intersection are negative, and we can argue the same thing, which is completely same. So that is in the subgroup, which that means it is symmetric about zero. I can visualize it, right? That is symmetric around zero. So that's what I can do. So in this case, H is dense. So think completely geometrically. Think everything geometrically. Okay. So if you don't understand the proof at any step, please comment. I'll reply. Okay. Because it might happen to understand this. It's not so clear. It might be okay. So you have to think it, that why this is true. So what we are using here, we are using here that any bounded below subset always have a infimum. That's a completeness property of R, right? Bounded above subset must have a supremum, and bounded below subset must have an infimum. So here it is bounded below, so we can do that. And for if you choose the negative real number, then you have to work with supremum. You have to work with supremum. Every proof will work, that is completely same. Okay. And then you are doing the same thing. I am considering the case where infimum is greater than 0, and the another case where infimum is equal to 0. If infimum is greater than 0, I need to assume two cases: infimum belongs to h, and infimum doesn't belongs to h. Okay, that's just two different cases, and I all possibility I giving all the cases and then show that h is cyclic. And if u doesn't belong to h, sorry, if infimum is 0, u equal to 0, that will imply that u doesn't belong to w. I'm considering w, so u doesn't belong to h intersection w in particular. So in that case, I'm already showing that this becomes cyclic, this become dense. Okay, that is basically the geometrical. Okay, thank you. I hope this is clear. So as a result, application, this year a question comes in jam. There is considering a set s plus m plus n root 2 such that m n belongs to z. So s is clearly a subgroup, right? S is clearly a subgroup. This is clearly a subgroup, because that was also a part of option, so everybody can do that. That is not an issue. M1 plus n1 root 2 plus m2 plus n2 root 2, that is basically same as m1 plus m2 plus n1 plus n2. And you can, in particular, you can show that 0 belongs to this s, because 0 plus 0 root times root 2, which is basically same as 0, that is inside that. M1 plus n1 root 2 implies that minus m1 minus n1 root 2, that is inside s also. So this is a subgroup. That means s is either cyclic or dense. So if you can show s is not cyclic, that will imply s is dense, right? So only work you have to do that s is not cyclic. Okay, that is kind of obvious. Why kind of obvious? Say it is generated by some element. Okay, so element looks like a plus b root 2. Okay, where a b non-zero both. Is it possible to generate 2a? Because 2a must be k times a plus b root 2. That will imply kb equals to 0, which will imply b equal to 0. That is not possible. So if it is generated by a, which is a is an integer, then root 2 cannot be generated by a, right? Again, if it is generated by b times root 2, that will imply that 2 cannot be generated by b times root 2. So that means in particular there is no generator. Hence, S is not cyclic. This will imply S is dense. So why this theorem is very, very important? Because if you want to show that this set m plus n root 2 is dense, that is extremely hard. You can do it by using analysis. You can use epsilon delta concept, and then you have to show that this intersects every interval. That is possible. There is proof of that, but that is extremely hard. But if you know this result, then you can do it. Uh, the, in previous year also there's question comes like that s prime equal to m plus n pi such that mn belongs to z. That is also the case. So in this case, s is not cyclic and s is dense. In particular, you can show in particular if s is m plus n t, where mn integer and t belongs to rational irrational, t is a irrational number, then clearly s is dense by the same property. It's a very strong result. I can prove it by using a simple group theory, which is quite easy, right? That's why it is very much interesting. Thank you. I hope this video will helpful to all of you, and so you can comment and please share the video. Okay, if you need any help, you can comment. Thank you.